Thank you. And share the screen. Can you see it?
Yes.
Yeah.
Okay, good. So let's get started. And, this is a very, very weird day. For those of you who are actually not here in Berkeley, it actually looks like this, 11 in the morning. I took this picture just an hour ago, just outside of home. So it's because of wildfire, it's smoke all over the place, and some places have power outages. So it's really apocalyptic, people say. If you're not in the area, you should be happy about it, at least for today. Anyway, so we did actually get to quantum field theory last week. So we started with this harmonic oscillator algebra. We decided to use this harmonic oscillator algebra to literally create a particle at a particular position in space. So we introduced this idea first by putting particles on a lattice, and we came up with this Lagrangian to represent that idea. We also made the particles actually move from one position to another. And that is thanks to this additional term in the Hamiltonian, so that you annihilate a particle at a given location. You create a particle at a nearby location. So this term in the Hamiltonian represents the motion of the particle. And by carefully choosing the parameters in this Lagrangian, we managed to take this continuum limit. So without having lattice anymore, the particles live in this free space. So psi of x is an operator that annihilates a particle at position x, and psi dagger of x is an operator that creates a particle at position x. They satisfy this commutation relation, which is now given by the delta function. And we came up with this term, which represents the kinetic energy of the particle. So now we have a quantum field theory, which means that psi of x is a field because it's a function of x, but it's also quantum because this actually satisfies this quantum commutation relation. It's an operator, it's not a number. Hence, this is a quantum field, and we are describing a point particles using this Lagrangian and resulting Hamiltonian. So that's the theory, namely that the whole thing is now a quantum field theory. So that's what I advertised on the day one of this course. You get to see this quantum field theory. Now it's actually, you're looking at it. And so we try to actually make use of this in a variety of situations. And so that's where we are. And this particular quantum field theory got a name. I call the Schrödinger field theory. And so if you have this Lagrangian, the first thing you do is to, of course, look at this term with a time derivative. And by differentiating the Lagrangian with respect to the time derivative of the variable or coordinate, we say, psi dot, you get IH bar psi dagger as its canonically conjugate momentum. So that gives you this canonical commutation relation that psi of x is the coordinate, IH bar times psi dagger is the momentum, which is supposed to give you IH bar with this delta function normalization. So I already canceled IH bar from both sides of the equation so that psi and psi dagger now do satisfy this algebra, relevant for annihilation and creation operator. So what we have done so far is actually worked it out backwards. So I'm basically giving you sort of the idea how you might have discovered quantum field theory, which nobody has done that before, by starting with this idea of the creation annihilation operator for particles, and we build up this Schrödinger field theory backwards. And so now that we have worked it backwards, later on, we actually do it sort of forward. So we have done this basically bottom up. Now we'd like to do is also top down. So that you'll see that both directions actually meet in the middle. But anyway, so this is the Schrödinger field theory. And once you're given this Lagrangian, then you can work out Hamiltonian with it. So this is the form of the Hamiltonian you get from this Lagrangian. And now that the psi and psi dagger satisfy this algebra for the annihilation and creation operators, we define the vacuum state that is annihilated by this annihilation operator at every position in space. Then you start creating this Fock space by acting the creation operator at various positions in space on this vacuum state. So you start with a state with no particles in it, you act creation operator once, you get a state with one particle in it. Or you acted twice, you have a state with two particles, three particles, four particles, and so on and so forth. So this is where we now know that psi of x is a quantum field. It's a function of space, that's a field, and it's quantum because it's an operator. But the reason why this particular theory is called the Schrödinger field theory is that because if you derive the Euler-Lagrange equation out of this Lagrangian by taking the variation with respect to psi dagger. So psi dagger variation actually gives you delta psi dagger multiplying IH bar psi dot minus 2m, h bar squared over 2m, and I have the spatial derivative of delta psi dagger. So I have to take the integration by parts to let this derivative act on psi instead, so that I can freely take out the variation with respect to psi dagger. So that gives you the differential equation. That actually turns out to be this equation over here, where I'm afraid I actually made a typo. This is a sign mistake, I believe. But the point here is that this equation looks exactly the same as the Schrödinger equation of free-point particle. And that resemblance made people call this Schrödinger field theory. And I come back and talk about this, the idea that the Schrödinger equation is actually an Euler-Lagrange equation out of field theory is very confusing. I even would like to say that's a wrong idea, and I elaborate on this more as in the next couple of slides. But there is definitely this resemblance that starting with this Lagrangian, Euler-Lagrange equation looks like it's a Schrödinger equation in quantum mechanics. So the reason I'm saying it's a wrong idea is that this is just, in some sense, a coincidence, because so far we only talked about a free theory. It doesn't have any potential. It doesn't have any interaction. And that's the reason why there's this resemblance between the field equation and the Schrödinger equation in quantum mechanics. It turns out the Euler-Lagrange equation from the field theory is actually a nonlinear equation in general. It doesn't satisfy superposition principle. It doesn't satisfy unitarity or conserved probability. So taking that as a wave function of the probabilistic interpretation turns out to fail in the end. So what we get from field theory, the Euler-Lagrange equation is not meant to be the Schrödinger equation of the quantum mechanics. And you'll see that distinction very clearly in the next couple of slides. But anyway, so at least you see the reason why people decided to call this field theory a Schrödinger field theory, because of the resemblance between the Euler-Lagrange equation you get out of this field theory to the Schrödinger equation of the free-point particle. So anyway, so that's the name. Any questions about this?
Yeah, I'm just thinking, what if we take the Euler-Lagrange equation with respect to psi instead of psi dagger? Then do we have the same like equation of motion?
Yep, that's an excellent question, and indeed you do. So if you take the variation with respect to psi, then for this term, you also need to do the integration by parts in time derivative, so that the time derivative dot acts on psi dagger instead. And here also, that you take the variation with respect to psi, so this spatial derivative would act on psi dagger instead by the integration by parts. So end result of that is just a complex conjugate of this whole thing. And that's not a coincidence. So this is because this Lagrangian is real, or Hermitian, if you're talking about an operator, up to a total derivative. So given the fact that Lagrangian is real up to a total derivative, guarantees that the equation of motion you get from variation with respect to psi and the equation of motion you get by variation with respect to psi dagger are complex conjugates or Hermitian conjugates to each other. So Euler-Lagrange equation is obtained either by taking variation with respect to psi or by variation with respect to psi dagger, and they end up being the same equation upon complex conjugation. Okay, does that answer your question?
Yes, yes, sure. Thank you.
Any further questions here?
When we do take the like the variation of the Lagrangian with respect to psi, we would still do the, I guess, the total derivative expansion with respect to both psi and psi dot, correct?
I'm sorry that you said total derivative expansion. What do you mean by that?
Or, like, so for example, in classical Lagrangian, you'd have the derivative of the Lagrangian with respect to Q plus variation in Q plus the derivative of the Lagrangian with respect to Q dot times the variation. So here we would perform the same thing, but Q replaced with either psi or psi dagger. But we'd still
That's
have
right.
the psi.
That's exactly the same idea. And the second term you mentioned, the derivative with respect to Q dot with time derivative acting on it, is the same thing as doing integration by parts first and then taking the variation. So you can do it either way.
Okay.
Good, thank you for that question too. Any further questions? Okay, so let me say a few more words about the Schrödinger field theory here. And one thing we did construct on the lattice is this the eigenstate of the momentum. And we can basically do the same thing with the Schrödinger field as well. So the idea is that this psi dagger of x acting on 0 is meant to be a localized state where particle is now created at position x. But when you want to create a plane wave solution, then you sum over the position eigenstate with a weight given by this wave factor, e to the ikx, where k is the wave vector in the position space, right? So this is the same idea as doing the quantum mechanics. And if you actually want to be sure that this is indeed the momentum eigenstate, and so what you can do is to act this Hamiltonian, which we got from this Lagrangian, on this state. And so let me back up once. So I just act this Hamiltonian, which is now written in terms of this field operator of psi and psi dagger. And I wrote it over here. And to avoid the clash of notation, I changed this dummy variable x, this is a dummy variable for integration, by y, so that this piece written for the Hamiltonian is in terms of y integral, while the state is now still written in terms of x integral, again, just for the purpose of avoiding the clash of notation. And what you're supposed to do is very simple. So from the point of view of the state, here's the vacuum state. You create one particle with psi dagger, and here's psi that annihilates that particle, but you create a particle again, so end result is still one particle state, right? Starting from 0, here's 1, and it's a -1 leads to back to 0, and +1 leads to +1, so the whole thing is still one particle state. And in order to work out what you actually get out of this, you use this psi annihilation operator and commute this with this creation operator psi dagger. And the reason why you can do this is that if you reverse the order, psi would be acting directly on the vacuum state. And by definition of the vacuum state gets annihilated by the annihilation operator. So replacing this del y psi dagger with the commutator gives you the term with the opposite ordering of psi dagger del y psi, but del y psi is acting directly on the vacuum, so the psi would annihilate it. So here I'm changing the order of these two operators by this commutator, but I have not any changes to the final result because psi acting on a vacuum would just identically vanish. But the purpose of rewriting the product of these two operators by a commutator is because for the commutator, we know what we are supposed to get. Psi dagger commutator is a delta function. So here I have a commutator of psi of y and psi dagger of x. And this derivative is only acting on psi because it's a function of y. So I can take this derivative out of the commutator, and psi dagger commutator becomes a delta function. So that's what I'm going to get. And using this delta function, I'd like to integrate over y. But the expression is still a little bit inconvenient because delta function has this derivative acting on it. But we all know that delta function vanishes at infinity. So here it is really justified to do the integration by parts. So I let this y derivative act on this psi dagger of y instead. And I get a minus sign because of that. And then 2 powers of y derivative would act on psi dagger. But now together with this delta function, which is now free without any derivative acting on it, then I can easily do a y integral so that all the y's in expression turn into x. So this is what I get after doing the y integral. And once again, I rely on integration by parts. And some of you pointed out actually the last time that it may not be strictly justified because the plane wave doesn't vanish at infinity. So here I'm being a little sloppy. So either you take the periodic boundary condition or you put in some Gaussian damping factor to make a wave packet, then you will be justified to do so. I'm skipping that step here. I'm being a little sloppy, but at the end of the result is the same. So I liberally use the integration parts by let this x derivative acting on x over here in the wave factor. So each x derivative then would extract ik from the exponent. So end result turns out to be this. So I have this number, h bar squared of k squared over 2m, and the rest looks exactly the same as the state we started out with. Hence, this is the eigenvalue of the state k under this Hamiltonian, which is written with this field operator. So it looks a little bit more cumbersome than what you're used to in quantum mechanics, where the momentum operator is just given by h bar times derivative. You can just readily let the derivative act on the wave function to get the eigenvalue. It's a little bit more complicated. It takes more steps, but end result is the same. So the state we constructed over here using the vacuum state with the creation operator with a superposition weighted by this wave factor e to the ikx really does have the meaning of one particle state with definite momentum given by h bar times k. And that's the de Broglie's relationship, right? So that's what we got at the end of the day. So any questions about this?
Just going from the third to last line to this, actually, no, going from the second to last line to the last line, that was an integration by parts, right? To move the spatial derivative onto e to the ikx?
That's right.
Okay.
Is that okay?
Professor, I don't fully understand how you replaced del y on psi y acting on the integral with the commutator.
This one here.
Yes.
Yeah, so let me first move this dx integral to up front. So that's this dy dx integral. And then what you have here is that you have the vacuum state and psi dagger x acting on it first, and this del y psi y acting on that next, and finally del y psi dagger y acting last, and the rest is just the number and the integrals. So all we have done from here to there is to use the fact that when psi of y acts directly on the vacuum state, it annihilates the state by the definition of the vacuum state. So every annihilation operator acting directly on the vacuum is supposed to give you 0. Because it has no particle in it, you can't annihilate any particle any further. So that's the same thing as the ground state in harmonic oscillator. The ground state cannot be lowered any further. So annihilation operator acting on the ground state is identically 0. So using that
fact.
You
just subtracted 0 off.
Yeah,
Okay.
exactly. So using that fact, inside this commutator, the first ordering of del y psi psi dagger is what I used to have over here. And then comes the other ordering. So negative psi dagger x del y psi acting on the vacuum state is identically 0 because psi of y is on the left acting directly on the vacuum state. So going from this line to that line, I have not changed anything. And that's the idea. Does that answer your question, Varun?
Yes, thank you.
Okay, good. Any further questions over here?
Yes, because I think like the line above h times cat k, the cat k is right there. There, I think the last term should be e to the minus ikx, because we're doing the Fourier transform from the position space to momentum space. We time the, I think we time the e to the minus ikx. So
No,
the cat
I believe this is right. So the energy dependence is e to the minus IET over h bar, and the plane wave factor is e to the plus IPX over h bar. So it should be really plus I.
But if we, so if we take the momentum operator to act on this state, we have like IH bar, partial, X acting on this, cat, then we if we act on this, act on this phase factor, we put out an I time, we have an I factor, right? And then 2I factor gives you a minus. So the eigenvalue should be minus k in front instead of
I'm not really sure. So when you write momentum operator in position space, it's h bar over I times derivative, right?
Yes.
So if you acted on the plane wave like this, then ik is what comes off the derivative, and you have h bar over I, so i's cancel, so you end up with h bar times k.
Okay, yes.
Is that okay?
Yes, I see.
Okay.
Yeah. Okay.
Good.
Okay, cool.
Any further questions on this slide? All right, so now we have learned how to write a momentum eigenstate using quantum field theory. Now I'd like to generalize this idea. So this is the momentum eigenstate for one particle, and this is what we do in quantum field theory. And let us just remind ourselves what we used to do in quantum mechanics, which is this. So momentum eigenstate can be written in the following way, where I use the completeness relation that position ket integrated over entire position possibilities is just one. It's a decompositional unity. And I hope that sounds familiar to everybody. If it's not, please raise your hand and ask questions about this. So using this integral over x with this xx ket and bra is meant to be 1. I can just freely act this 1 on the momentum eigenstate. So these two are meant to be the same. And what in turn means is that this xk inner product is about representing the momentum eigenstate in the position space. And this is the wave function of the momentum eigenstate. And that's why this is supposed to be just e to the ikx. And people use different notations about this. Maybe you have seen the factor like square root of 2 pi in the definition. Here, I'm not really paying attention to that overall normalization factor. The main point I'm trying to make is that momentum eigenstate in quantum mechanics is given in terms of a superposition of the position eigenstates weighted by the wave factor e to the ikx. This is exactly the same idea we used in quantum field theory. So psi dag over x acting on the vacuum state gives you a position eigenstate of a single particle. And then I'm taking superposition of that position eigenstate with this wave factor e to the ikx. So they are really in one-to-one correspondence. Namely, psi dag of x acting on the vacuum state is really meant to be the same thing as this position eigenstate x in quantum mechanics. And what multiplies the position eigenstate is supposed to be the wave function, which we have learned a lot and used a lot, the good old wave function that's out of the Schrödinger equation. So the wave function is supposed to multiply the creation operator in the case of quantum field theory. So that's the new aspect. What we used to do in quantum mechanics is that we live in a Hilbert space of single particle. We choose the position representation of the quantum mechanics in this abstract Hilbert space. And in that representation, the coefficient of the position eigenstate is the wave function. In a QFT, we start with a vacuum, and by using this creation operator, you now go a notch up in Fock space, which encompasses all possible one-particle state. And again, using this linear superposition of the position eigenstate in this one-particle subspace of the Fock space, you can use this wave function to describe the state you want. The reason I'm emphasizing this point now is that by using this idea, I'm allowed to go freely into multi-particle state too. So in quantum field theory, now I can define two particle states, and both particles have definite momenta. So starting with the vacuum state, I create one particle at position x2, I create a second particle at position x1, and here again, I take linear superposition of these position eigenstates weighted by these wave factors, which is supposed to give you this energy eigenstates given by the energy of two free particles. So first particle has momentum h bar k1. So this is p squared over 2m for the first particle. The second particle has momentum wave vector k2, therefore momentum h bar k2. So p squared over 2m kinetic energy is given by this. And what you can do is, again, literally take this Hamiltonian written in fields and let this Hamiltonian act on this state. And by, again, using this canonical commutation between psi in the Hamiltonian with either of this psi dagger, you find this is the eigenvalue. So this is the way you get what you used to have in quantum mechanics using quantum field theory language. And reminder here is that what you do in quantum mechanics is, again, exactly the same thing. The momentum eigenstate for two particles can be obtained by the position eigenstates of two particles weighted by this wave function, which is e to the ik1 x1 times e to the ik2 x2, right? So this is what you do in quantum mechanics. Once again, you see this one-to-one correspondence between position eigenstate you created in quantum field theory and the position eigenstate you define in the quantum mechanics. And both of them are weighted by this wave function, e to the ik1 x1 times e to the ik2 x2. So what I'm trying to tell you here is that we started with a totally different way of constructing Hilbert space. You start with a vacuum state, you use this creation operator to create one particle. If you do it twice, you get two particles. But no matter how many particles you create, the idea is still the same. You first create particles in position space. You weight that with the wave function and take linear superpositions of all these position eigenstates with the wave function as a weight. And that is supposed to represent the state you dealt with a lot in quantum mechanics class. But there is one small difference which can be important, because when you actually create a state like this in quantum field theory, we know psi daggers commute with each other. So the ordering between x1, x2 doesn't matter. It is symmetric under interchange of x1 and x2. That's not necessarily clear in quantum mechanics. If you have two position operators and their eigenvalues x1 and x2, it's not automatically symmetric under interchange. As a result, if you're talking about two identical bosons, you have to add the different ordering by hand and symmetrize it. So that's one additional step you have to take. On the other hand, in quantum field theory, because this psi dagger of x1 and psi dagger of x2 commute with each other, it doesn't matter which order you write it, and therefore the wave function is automatically symmetrized. So that's the main difference between quantum mechanics and quantum field theory, but otherwise you see exactly the same idea. So I hope this makes sense. Quantum field theory we came up with. appears to have exactly the same physical content as multi-particle quantum mechanics. But it's different in two accounts. One, you don't need to specify the number of particles to come up with a Hilbert space. In quantum mechanics, you have to specify how many particles you have and then construct the Hilbert space according to position operators of each of the particles. You cannot change the number of particles by any means. In QFT side, you can, because the states with different number of particles are contained in this same huge Fock space, that's a Hilbert space of QFT, and you have these operators, psi m, psi dagger, that can change the number of particles up and down. So all of these states with different number of particles are contained in the same Hilbert space. So that's one big difference. And that, in the end, would allow us to talk about processes where number of particles can change, like emission of photon, absorption of photon. Second, it has this quantum statistics built in. The wave functions are automatically symmetric under interchange of identical particles. So this is what you have to force by hand in the case of quantum mechanics. By interchanging particles in the wave function, you sum them up to make sure that the total sum is symmetric under any interchange. But on the QFT side, that's already built in. So let me just repeat. There are two major differences between quantum mechanics and quantum field theory. One, the number of particles can be changed in QFT, while it cannot be in quantum mechanics. And second, the symmetrization of the wave function is automatic in QFT, but you have to do something about it in quantum mechanics by hand. But apart from these two major differences, the physics content of QFT is exactly identical as the multi-particle quantum mechanics. Okay, so here we are making a lot of conceptual issues about how you go about and deal with the quantum theory, either by quantum mechanics or quantum field theory. So I believe this is a good time to stop and pause for more questions. No questions? I'm surprised. Go ahead.
Yeah. So in Fock space, you can dynamically add particles, but in Hilbert space, it's like static. It's predefined in a sense.
Right. Because there's no way, if you have a function with, let's say, 100 arguments in it, the function of 100 arguments would jump to another function with 101 arguments. That's mathematically totally ill-defined. But on the QFT side, you do have these operators that are designed to change the number of particles from the onset. So you can freely talk about processes where number of particles actually do change. And that's really the major advantage of talking about QFT. It turns out that we will also talk about situation where your state is really weird, linear superposition of states with different number of particles in it. It turns out that you actually do want to use a state like this for certain purposes. And that's also totally impossible with the quantum mechanics where number of particles is fixed in a given Hilbert space.
So the correspondences that we're seeing here, we're only working with certain subspaces of the Fock space that are analogous to like constant number of particles in quantum mechanics. But this is just a subset. In reality, we can dynamically change the size while we're working through it, right? By just adding, applying the creation operator.
Absolutely, that's completely correct. Yes, thank you for making this concise summary. Any further questions? So I'd like to hammer. Okay, go ahead.
Sorry, I have questions. So can you say something about why quantum mechanics doesn't have the built-in symmetry and why QFT does? And also, how does QFT deal with fermions?
Yeah, so how to deal with the fermions is something I'm going to talk about later. So the basic idea is that there is actually two ways of quantizing this Lagrangian. The one of them is this one with psi-dagger commutator. But it turns out that there's another way of consistently quantizing this Lagrangian using what is called anti-commutator. The commutator of two operators, A and B, is AB minus BA, right? That's something you have seen in quantum mechanics class. But anti-commutator is AB plus BA instead of minus BA. And if you use that way of quantizing this Lagrangian, it turns out that that will lead to a theory of fermions where the wave functions are automatically antisymmetric under the interchange of particles. So we'll come back and talk about this later. So don't worry about that. And the first question, I'm not sure I got. Can you repeat that first question again?
I just wish you can say something on why QFT has the built-in symmetry, whereas quantum mechanics doesn't have.
Yeah, so when you define this quantum mechanical state, x1, x2, it's not necessarily true that x1, x2 state and x2, x1 state are the same. So that's something you have to impose by hand. If you are dealing with two identical particles, you say, you take the state x1, x2, and you add the state x2, x1, and on the sum, you take the normalization of 1 over square root 2, and that is the symmetrized state. So in addition to solving for example, eigenvalue equations for both Hamiltonian and momentum and so on and so forth, at the end of the day, you also need to do this symmetrization by hand. But in the case of QFT, the minute you create this two particle state out of the vacuum using two creation operators, x1 and x2 can be freely interchanged, and it stays the same state because these two operators commute with each other. So that's what I meant by saying that QFT has this quantum statistics built in. You don't need to do anything to symmetrize the state by hand, like what you used to do in quantum mechanics. Does that make sense, Tom?
Yeah, thank you.
Okay, good. Any further questions here?
Yes.
Oh, sorry, go first.
Okay.
Elijah?
So,
Oh, no, Ryan, you can go first.
Oh, okay. All right, Ryan.
okay. So how can you like use the two dagger operator to create the cat x1, x2? Because you said that it's automatically symmetric. So to me, psi dagger x1, psi dagger x2 acting on the vacuum is just square root of 2 and linear combination of the x1, x2, and x2, x1. So how can we use these two operators to produce x1, x2 cat, like these states building?
So what I'm
Can we
saying
do that,
is that
or
what I'm saying is that psi dagger x1, psi dagger x2 acting on the vacuum already corresponds to x1, x2 plus x2, x1 over square root 2.
Yes, I know that. So my question is, can we like use these two operators to produce x1, x2, these states only? Like, can we do that?
I'm not sure I understand. What do you mean by deduce?
No, produce, sorry.
Or produce?
Yeah.
I'm not sure I still understand the question actually.
Because you use these two operators acting on the vacuum, you get a symmetric state automatically. Right? So, but can we use these two to get the cat, like this cat, the cat x1, x2 lives in this Fock space. But can we use these two operators to build this state out of the vacuum?
Are you asking a question how I can produce a state where x2 and x2 are not symmetric? Is that the question?
Yes.
Yeah, so that's an excellent question too. So if x1, x2 are not symmetric on the interchange, then you are not talking about identical particles. You're talking about two different kinds of particles like electron and proton instead of two electrons, right? And so in that case, you need to introduce separate field for different particles. So single field psi always produces identical particles. No matter how many times you use psi dagger to create more particles, particles created are always identical because they came from the same field operator. But if you talk about two non-identical particles, you need to start with a theory that has two different fields in it. So one field corresponds to, let's say, electron field. So use the creation operator, create 1 electron, 2 electrons, and so on and so forth. You have another field, which corresponds to proton, which you can use to create 1 protons, 2 protons, 3 protons, so on and so forth. but they are two different fields. So when you act two different fields on the vacuum state, so this is psi1, this is psi2, then interchanging two positions would change your state because they still commute, but they refer to different positions, so they are not identical states anymore. So that is the way you can create a state that will correspond to position eigenstates of two non-identical particles where the state is not symmetric under interchange because they are not identical. Does that answer your question, Brian?
Yes, kind of. So that means if they're identical particles, we are never able to use like two daggers to produce a single cat x1, x2. We are only able to produce their symmetric form, right?
That's correct, right.
Oh, okay, yeah, okay, I see.
Good. Elijah?
Yeah, I was just gonna ask why we need to symmetrize the exponential part in the like quantum mechanic case, but in QFT we just leave it as like EIK1x1, EIK2x2 because it's not symmetric under interchange, right? Of like x1 and x2.
Right. So suppose you actually interchange K1 and K2. Then you remember that x1 and x2 are dummy variables for the integration. So then I can relabel x1 by x2 and x2 by x1. So if I do that, then what results is that this turns out to be x dagger of x2, x dagger of x1. But because these two operators commute, I can commute them and without changing the state. So that ends up being the same as what I started with. So that's the way you can show the state K1, K2 defined this way, even though I don't symmetrize it, turns out the same as state K2, K1.
Okay.
Does that make
would
sense?
it be like equally valid to switch x1 and x2 and leave k1 and k2 stationary? Like, is that an equally valid way of saying you're switching the two particles?
Yeah, so if you don't talk about momentum eigenstates, but only talk about position eigenstates, you don't have this integral. You just have this thing in Sion box. This is the position eigenstates of two identical particles of position x1 and x2. So I will call this x1, x2 state, like what do you do in quantum mechanics. Then I can ask the question, what is x2, x1 state? Then I have psi dagger x2, psi dagger x1 acting on vacuum. But because these two operators commute, I can interchange the order. And that's the state I started with, x1, x2. So you can see that this is an invariant under interchange of two particles, both in position state, that's the Sion box, and also in momentum space, which is this whole thing.
Okay. Thanks.
Okay. Any further questions?
Yeah,
so,
I don't
yeah,
know
go
if
ahead.
this is myself, but so I see now how QFT preserves like the symmetrization without needing to like actually symmetrize the wave function. But like at least in 137b, the reason for symmetrization was always kind of deferred to quantum field theory, like the spin statistics theorem, I guess. Does that follow from this as well, or is that a completely different discussion?
You're getting at a very important point. So in quantum field theory, there's something called spin statistics theorem that says that every particle with integer spin is a boson, and every particle with half-odd spin is a fermion. And so that is related to what we are doing over here, but that will come up only when we get into the relativistic quantum field theory. Without relativity, we don't have spin statistics theorem. Only when you go to relativity, you find additional consistency requirements that forces you to treat integer spin particles as bosons and half-odd spin particles as fermions, and we don't see that yet. So all we can see right now is that QFT has the quantum statistics built in. That's something you can see here. But whether you are supposed to choose this commutation relation or anti-commutation relation, we will come back and talk about this later for fermions, that's an arbitrary choice at this stage. But when you go to relativity, then it wouldn't be a choice, that would be forced upon you.
Okay, thank you.
All right, so let me then move on. So now we have seen that the QFT has the same content, physics content, as a multiparticle quantum mechanics, but so far we have demonstrated it only for the momentum eigenstates. And it turns out it's actually much more general than that. So here's the dictionary. So what you do in quantum mechanics for multiparticle state, x1 dot 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 xn, is again, we use this completeness relation. So from this integral symbol all the way up to here is meant to be 1, just a completeness over all position eigenstates for n particles. And this piece here, where you take the inner product of position eigen bra with the state itself, is the wave function we know and love. So we still have this idea that arbitrary state can be written as a linear superposition of the position eigenstates weighted by the wave function. In a previous slide, we had this particular choice of the wave function that corresponds to this momentum eigenstates. But if we have a more complicated situation with some potential and interactions and so on and so forth, this statement is always true because all I use is just the completeness relation of the position eigenstates. So what you do in QFT is of course the same. So you replace this position eigenket by a state where you act this creation operators n times on the vacuum state. So this creates an n-body state with definite positions. So that's why physics content is the same as this position eigenstates. I'm sorry, I went too far. Oops. I lost track of it. Where did I go? Yeah, that's right. And so this n creation operators will create n particle state. So this is meant to be analogous to this position eigenstates for n particles. And you take linear superpositions of these position eigenstates using the wave function as its weight. So the correspondence is always this. In quantum mechanics, you introduce this wave function, but in QFT, wave function appears as a weight when you take linear superpositions of position eigenstates. That's why I'm trying to make distinction between this capital psi, which is meant to be wave function, which obey the linear Schrödinger equations, while little psi is an operator which corresponds to creation and annihilation operators of particles. So this little psi and this capital psi have totally different meanings. And unfortunately, this is the standard notation in the literature. That's why it's kind of maximally confusing. And the equations they obey also look similar. That's even more confusing. But here I'm trying to make a very clear distinction between wave function and psi operator. Psi operator is annihilation and creation of particles at a position x. That's what psi and psi diagonal operators do. And once you have done this, you take linear superposition of them using this wave function capital psi, and that's what you do in quantum mechanics. So little psi and capital psi have totally different meanings. Unfortunate notation literature is the same psi, but they mean totally different things. And that's the point I want to hammer on over here. Any questions about this? I hope this is clear. Okay. And if that's true, then we should be able to actually use this to the next level. So right now we have this situation of this Lagrangian leading up to this Euler-Lagrange equation, which resembles the Schrödinger equation of the free particle. So at this point, it may look like the Schrödinger equation can come out from this classical Lagrangian. And then that leads to this, I would say, the wrong name called the second quantization. So it may look like you have this Lagrangian of the point particle first, and that will give you this Schrödinger equation after quantization. And then you find this wave function psi. So this is quote unquote first quantization. And for some obscure reason, let's say we're going to quantize this wave function psi next by building a Lagrangian that would reproduce the Schrödinger equation. And then using this Lagrangian, whose Euler-Lagrange equation happens to be Schrödinger equation, we quantize this once again using this canonical quantization condition. That's why this is the second quantization. Often, many books describe it that way, but what we have seen is this is the totally wrong idea, because the Schrödinger equation is not meant to be a Euler-Lagrange equation from a field theory Lagrangian. And I will show you a counterexample to this idea next, so that you would appreciate this point better, I hope. But anyway, so this is the terminology often used in the literature. So dealing with a quantum field theory is said to be second quantization, because it looks like as if you first do the quantization to get the Schrödinger equation, then you regard this Schrödinger wave function as a field operator, and that's the second quantization. But that's not the idea, and by showing a counterexample next, I hope you would appreciate that point. Any questions about this? So I keep using this expression of the wave function capital psi that multiplies an n-body state you created using little psi dagger. So little psi is really creation annihilation. Capital psi is the wave function. And with this capital psi that follows the Schrödinger equation when you go to quantum theory. And the little psi is really meant to be a field from the grounds up. This psi is not meant to be what obeys the Schrödinger equation. So that actually brings up the interesting question, right? So now that I told you this little psi is not meant to follow the Schrödinger equation, it obeys certain wave equation. What is the classical limit of this psi? But anyway, so to see this, it's actually very useful to introduce interaction. So far we talked about the free particle. Now let's introduce interactions. So let us get started with the easy part of the interaction. So suppose these particles have to move in some kind of potential energy. So here I depicted a three-particle state, going back to the lattice example of position 5, 6, and 14. And let's imagine that these particles live in some kind of potential energy V of x. Then the Hamiltonian you want would have energy for each particle you created. So that's what I called h bar omega the last week. So I have three particles, so that gives you 3 h bar omega when you created three particles. But each particle now lives in this potential energy, so there should be additional contribution to the energy, where this particle experiences potential energy at position 5d, this particle experiences potential energy at position 6d, and this one at 14d. So the Hamiltonian should include these potential energy contributions. So I need to modify this Lagrangian to make that happen, and that's very easy to do. All you have to do is add this term minus v of x a dagger a at that position. Namely that if you use this Hamiltonian, of course this is Lagrangian, so Hamiltonian has plus sign instead. If you use the Hamiltonian a dagger n, so this a dagger n counts the number of particles at position 5d. At that position, you evaluate this potential. So that gives you this contribution to the energy. And a dagger 6a6 counts the number of particles at position 6. Is multiplied by the potential energy at that position, so that you get this contribution to the energy. And a dagger 14a14 gives you 1 for this position 14, again multiplied by the potential energy. But if you choose n at any of the different positions, a dagger a vanishes, because you haven't created a particle there. A dagger a acting on the vacuum state give you 0. That's a number eigenstate. So just by modifying the Hamiltonian to add this term, you successfully can describe the situation where particles move inside the potential energy. So that's the new Hamiltonian now. And this works even in a situation where two particles happen to live on the same position. So in this case, at site 6, a dagger a is 2 because you have two positions over there. And correspondingly, you are supposed to have twice the potential energy at that position. But at position 14, you still have only one particle. You count the position of potential energy only once. So in this case, the total energy will be 3 by h bar omega for creating 3 particles, plus V at position 14D for 1 particle, and V at position 6D twice for 2 particles that experience the same potential energy. So this Hamiltonian indeed correctly describes that situation as well. So describing particle living in the external potential is very easy. You just add a piece to the Hamiltonian that gives you potential energy evaluated at the position times A dagger A for that particular site. And then it's easy to see how you take the continuum limit. So all you need to change to the Lagrangian is to add this term where V of x is what is V of x here. And psi dagger psi is the number operator at position x that replaces A dagger n in this discrete lattice. And you sum over n for A dagger n. And correspondingly, you integrate over x for psi dagger psi of x. So that's the Lagrangian we use for the particles living in the external potential. Now, I advertise this discussion motivated by the fact that interacting theory may make it different between Schrödinger equation and Euler-Lagrange equation for the field. At this stage, it still looks the same. If you take variation of the Lagrangian with respect to psi dagger, you find this Euler-Lagrange equation. This still looks like it is the Schrödinger equation for a single particle in a potential energy V of x. So far, we haven't come up with a counterexample yet, but we will on the next slide. But anyway, one point we learned here is now we know how to talk about the particles living inside a potential energy V of x using quantum field theory language. So that's one thing we learned on this slide. Any questions about this?
I just had a very quick thing on the last slide in regards to the first and second quantizations. Yeah, so in regards to first quantization, shouldn't the psi be a capital psi? Because this is the wave function that we're dealing with instead of the operator.
So here I'm just giving you what have confused people. So when you write the Schrödinger equation and in quantum mechanics class, you typically use little psi, don't you? So that I use that notation here. And it's unfortunate that it's little psi we use for the quantum field theory, as you see in this Lagrangian over here. And that's part of the source of the confusion, I would say. So this is what causes confusion, and I try to clear up this confusion. I hope that makes sense.
Yeah, makes sense. Thanks.
Okay, good. Any further questions? So at least we have learned how to introduce potential energy for particles living in it. And then you can use the quantum field theory in the continuum limit to describe such a particle living inside this potential. So I made all this animation so that it takes long. But anyway, so that's how far we have gotten so far. But still, we have the situation that the Euler-Lagrange equation from the field theory looks the same as the Schrödinger equation for the wave function for single particle. Next slide would break this barrier. Now we talk about the repulsive interaction among particles. So in addition to the fact that the particles might be living in external potential, maybe coming from some kind of proton outside, which gives you the Coulomb potential or something like this. Now I also would like to describe the interactions among the particles we're dealing with. So what it means is that, well, for single particle, you may have just h bar omega, 2 particles, 2h bar omega, 3 particles, 3h bar omega, as long as the particles live on different sites. But if they come on top of each other, not only that you have 3 particles, but you have additional energy U, so that energy becomes higher when 2 particles come on the same site. So that's a situation where you increase the energy when particles come together, which means the particles want to be away from each other to lower energy. So that's the way you can describe a repulsive interaction among particles, right? So if you have two particles in position x1 and x2, when the energy increases when x1 and x2 come together, then that's the potential energy between the two particles, and that will represent the repulsive interaction. So what we would like to do is modify the Lagrangian we have now getting quite a bit getting used to, and see how we can represent this situation where you increase the energy when particles come together. And that can be done by adding this term. Now, this looks very different from the kind of terms we used to have. All the terms we used to have is 1 power in annihilation operator and 1 power in creation operator. Here again, 1 power in annihilation operator, 1 power in creation operator. But the new term I introduced have 2 powers in annihilation operator and 2 powers in creation operator. And the reason why this is useful is by this simple observation. As long as the particle occupying a given site is 1 at most, if you apply this operator on that site, because you have 2 annihilation operators acting on that state, the state with 1 particle is lowered to 0 by the first annihilation operator, but second annihilation operator make it vanishing because you can't lower it any further. So as long as you are dealing with 1 particle state on whatever side you like, this operator always give you 0, so no contribution to the energy. But if you have 2 particles on the same site, then you can use 2 annihilation operators acting on that site, and first annihilation operator give you 1 particle state with a normalization factor square root 2. Second annihilation operator would lower it further to the ground state or the vacuum state, still with this normalization factor square root 2. Then use the creation operator twice to bring it up to 1 particle state, and then further up to 2 particle state. And second creation operator gives you another normalization factor of square root 2. So you end up with the same state with 2 particles with eigenvalue 2. So by using this operator here, A dagger AA gives you 2 for 2 particle state. That cancels the factor 1/2. So you get additional contribution to energy given by U. So that's exactly the situation we wanted. So this is the Lagrangian that gives you the Hamiltonian in such a way that when 2 particles coincide on the same position, then you get additional contribution to energy given by U. And because the particles want to minimize the energy, you prefer the situation where 2 particles want to be on a different site, and therefore this is a situation that will represent the particles are repelling each other. And that's how you can introduce an interaction among the particles in this system. Okay, any questions about this idea?
Can you just repeat that last part again about
okay.
how the repulsive? Yeah, just the very last part.
So adding this term to the Lagrangian, or the positive sign of this term to the Hamiltonian, you now found the situation where putting 2 particles on the same site will give you additional contribution to the energy plus U. If you move this particle to the neighboring site, they no longer occupy the same site. So this A dagger AA operator doesn't give you any new contribution. So you're back to this situation without this additional term U. So if you are these 2 particles, if you come to the same site, it costs you additional energy U. Pun not intended. So this plus U is the additional cost of the energy you have to pay when 2 particles come together. So to minimize energy, it's better off for 2 particles to be away from each other, living on different sites, What that means is that there's a preference for particles to be scattered on the different sites rather than coming on top of each other on the same site. And that is the repulsive interaction. Does that make sense?
Yes, thank you.
Okay. Any further questions on this?
Yes.
So go ahead.
Can I ask? Yeah. I see you're only considering the situation where you get this potential if two particles reside in the same coordinate at the same coordinate.
Right.
But what would it look like if there's a distance dependency or like actual repulsive looking electromagnetic force or something like that?
Good. That's an excellent question. So for example, if all of these particles are charged, then there's a Coulomb repulsive potential among these particles. So we need to figure out how to represent that kind of situation too. So I will come back and talk about this later. So please bear with me for now. Here we are talking about only the short range repulsive interaction, and we learn how to deal with it first, then extend that later to the case of long range interactions. And then there's definitely a way of dealing with that too. So right now, please bear with me and let me move forward. Thank you for asking the question, by the way. That's an excellent question to ask. Any further questions at this stage of dealing with this repulsive short-range interaction? By the way, this is the kind of term the condensed matter physicists use on the lattice, really representing the strong repulsive interaction among the particles, short-range repulsive interactions of particles living in a crystal. So this is an example we actually use for practical purposes in condensed matter physics. But we will take the continuum limit next. Any further questions on that? Okay. So now we have this new Hamiltonian, which has this additional term, which looks unusual because it has 2 powers of annihilation operators and 2 powers of creation operators. So we now have this interacting theory, and we take this continuum limit, as we have done before. So we need to be careful about taking the limit because everything scales differently on the powers of this lattice constant d. So it turns out that what you need to keep fixed is the product of u times d when you take this limit. And the reason being that these first 2 terms have only 2 powers of a. So using this scaling with factor of d to 1/2, then a dagger a spits out factor of d that becomes part of this integration volume dx when you take this Leibniz limit of stretching out sigma to this integral symbol. But in the case of a dagger AA, that spits out 2 powers of d out of that, and only 1 power of d should be absorbed into this integration volume. So that leaves another factor of d hanging out there. So you need to make sure that the u, that's energy, times d, that's a lattice constant, is held fixed when you take the limit of the continuum. So by taking the limit, you find this continuum quantum field theory Lagrangian, which now has this psi dagger, psi dagger, psi psi term in it. This makes a huge difference when you actually take the Euler-Lagrange equation, again, by taking the variation with respect to psi dagger. So the first 2 terms are the same as before. By taking variation with respect to psi dagger, I get IH bar psi dot. I find a typo that this factor y shouldn't be there, and neither here. And taking variation with respect to psi dagger, again doing integration with parts, I get second derivative acting psi. So far the same. But for the last term, I take variation with respect to psi dagger. Because I have 2 powers psi dagger, I can take variation of either of them. So that gives you factor of 2, that cancels factor of 1/2. And then the other psi dagger, I didn't take variation of, remains. And 2 of the psi's still remain. So I find this as the Euler-Lagrange equation. Now you notice a new feature in here, namely that this Euler-Lagrange equation is non-linear in psi. So you do not have superposition principle for the field operator psi. Suppose you have one solution to this Euler-Lagrange equation, psi 1. You have another solution to Euler-Lagrange equation, psi 2. And in Schrödinger equation, you know and love, if you have two solutions, the sum of the two solutions are always yet another solution. Hence, you have the superposition principle. But with this nonlinear Euler-Lagrange equation, this is not linear. So psi1 plus psi2 is not a solution to this equation anymore. There is no superposition principle. So the fact that quantum field theory Lagrangian would lead to nonlinear Euler-Lagrange equation is the telltale sign that you cannot interpret psi as a wave function of the quantum mechanical Schrödinger equation. It's a different beast. So if you take this idea that this is the second quantization, then Lagrangian has to reproduce the Schrödinger equation in quantum mechanics, but it doesn't when the particle has a self-interaction with each other. So as UK already pointed out, this is a very particular type of self-interaction where the interaction is short-range. But nonetheless, already for this particular example, you see the fact that this is not second quantization. This is a brand new thing. You are dealing with Lagrangian of a field, and this Lagrangian is not quadratic in field, has a quartic term in it. And thanks to this quartic term, the Euler-Lagrange equation is nonlinear, has a cubic term in it. And this is not meant to reproduce the Schrödinger equation we get in quantum mechanics. This field is not wave function. This is something different. And we know what it is already from construction. Psi is meant to be creation annihilation operators of particles. It's not meant to be a Schrödinger wave function. It's a different thing. And you know this already, but this is the first example where you clearly see that these two are different beasts. Okay, any questions about this? Again, these are fairly conceptual issues. It's a very likely place where you get confused, and I got confused myself when I was learning this stuff myself, and that's why I'm trying to make this distinction as clear as possible, but you tell me if that is clear or not.
I just had a quick question on
Go
the
ahead.
sign of U. So isn't it the case that we're going to induce a positive energy penalty if there are two particles at the same site, and hence our like energy should increase?
That's right. That's the definition of U here. And if you have an attractive potential interaction instead, you choose U to be a negative number.
Okay. So why exactly is there then a negative sign in front? Like how?
Because the Lagrangian has negative of Hamiltonian in it.
Mm-hmm.
Remember, Lagrangian is PQ dot minus H. So this whole thing is minus H. So H is plus this and plus that.
Oh, okay. Yeah, I just got, I guess, confused on like, because we had a parentheses like halfway through.
Right.
Yeah.
Right.
Okay, makes sense. Yeah.
Okay. Thank you. Any further questions?
Yes, I'm just confused about this UD factor.
Uh-huh.
I thought if D is going to 0 and U is some positive constant, then why doesn't that term just vanish?
Yeah. So because we're taking this continuum limit, the idea that it costs you energy U when two particles come together becomes ill-defined in the continuum space because it basically becomes a delta function. And delta function has a normalization that when you integrate over the space, you get 1. So that is represented by U times D. So integration over space is multiplying D in this continuum limit. And that integral is what you want to keep fixed when you take the continuum limit. And you'll see that more explicitly on the next slides. So I hope you bear with me for now. And then you will see explicitly why keeping this U times D fixed is actually what's going to make sense in the continuum theory on the next few slides. So thank you for asking the question, and bear with me for now.
Where does the second I factor come from?
Yeah, so this is wrong. So this is a typo. I'm sorry.
Oh, okay.
I will fix that when I post the slides. Okay, any further questions? So I hope this distinction between field operator psi and wave function capital psi becomes very clear by really working out the Schrödinger equation of the field theory, where you see that these things are different from each other. So what we do is the same thing we have done before, using these creation annihilation operators, and then you actually build the wave function of it. But before getting to it, I'm just reinforcing this idea that this Euler-Lagrange equation is definitely not Schrödinger equation because it's nonlinear. And I don't know why it didn't come out correctly. Sum of two solutions is not a solution of this Euler-Lagrange equation. That's what I meant to say over here. So this equation is meant to be some kind of wave equation where it only makes sense after quantizing this field operator psi. So psi is really meant to be creation and annihilation operators of particles. So what we see here is the opposite from what we have done in quantum mechanics. This is some kind of wave equation. I don't know what this means yet. We don't know what this means yet, but somehow by quantizing this field or wave psi, you get particles out because this is the creation annihilation operators of particles. So what we have done in quantum mechanics is you have Lagrangian or Hamiltonian of particles. When you quantize it, you get the wave equation now. That's the Schrödinger equation. On the other hand, what we do in quantum field theory is that we have this Lagrangian that has this wave equation for field psi. And by quantizing it, and you quantize the wave or field and find particles out of it. So in quantum mechanics, you start with particles, you get set up this quantum commutation relation, and you get the Schrödinger wave function out. So you go from particles to waves. But in quantum field theory, you go from a classical wave equation to particles, namely that you have this wave, but you use this psi to now create particles. And that's something I mentioned to you on day one of this course. We know the quantum physics tells us every particle is a wave, every wave is a particle. So none of them is pure particle or pure wave, but we human beings are mere mortals. We don't know how to describe this weird object, which is simultaneously a wave and a particle. So we have to start somewhere. And what you decided to do without being told in quantum mechanics class is that you decided to start with the particle and then quantize it to get the wave out, and you end up having the matter wave. On the other hand, we can also decide to start with a wave instead. And then you have a classical theory of waves, and we will see what this wave represents later on. But you start with a classical theory of wave, you quantize it, and get particles out of it. And both of them are perfectly valid. But it turns out that doing the second way, starting from the wave to get particles out, turns out to be more useful to describe situations we're going to encounter next. But anyway, so again, this is a very conceptual point in QFT, but I hope this point is loud and clear. Okay, and because you also have to solve the homework problem, let me actually just go ahead and do one thing, where I hope to actually do the poll, but I lost time of it. So let me just show you one thing where you're supposed to deal with a homework problem. So this is what you're supposed to do. So you first create one particle state, and you can verify that's one particle state because it's an eigenstate of this number operator, psi dagger psi integrate over x. That's the generalization of a dagger n summed over all sites in the case of the lattice. And I told you already that arbitrary one particle state is given by a linear superposition of this one particle state weighted by this wave function capital psi. Then what you can do is literally act the Hamiltonian, including the self-interaction, acting on the state I defined on the previous slide. And Schrödinger equation is the same in quantum field theory, namely that time derivative of any state you like is given by the action of the Hamiltonian. So this is really the principle of a Hamiltonian being time translation operator. So this is the same either in quantum mechanics or quantum field theory. What you do is to work out the both sides. Time derivative acting on state. Time dependence is only on this wave function part of the state. So that's what you get, time derivative of the wave function. On the other hand, Hamiltonian is given by this field operator. And this is a little complicated part. You act this field theory Hamiltonian on the state you created. It turns out though that what we are dealing with right now is only a single particle state, only one power of psi dagger. If you have the self-interaction part, which is 2 powers of annihilation operator, you go up, down twice, you get 0. So you don't get any contribution from this term. You do get contributions from the first 2 terms. And then if you work out, you find this result. So this is the one particle Schrödinger equation on wave function you correctly reproduce from quantum field theory. And that's the exercise I want you to follow through in the homework problem. So we now have a nonlinear theory which has self-interaction. Euler-Lagrange equation is not the same as the Schrödinger equation. But if you work out the correct Schrödinger equation in field theory, then the wave function of the field theory still satisfies the correct one particle Schrödinger equation, which is indeed linear in capital psi. So I stop here, and this is what I'm asking you to do in homework problem. And if you have any further questions, ask me now, or you can also email me. And also I try to repeat this exercise on Friday's class. Okay, so let me stop sharing it. Any questions?
Sure. I guess just a broad conceptual question about the second last slide.
Okay.
You said we start with waves and go to particles, but the creation and annihilation operators came from the simple harmonic oscillator for particles, right? From like vanilla QM. So are we just using that as a motivation to start with creation and annihilation operators from scratch, or is the harmonic oscillator for particles in some way fundamental?
Yeah, so harmonic oscillator I introduced as a sort of heuristic way of discovering quantum field theory. But as you remember, we started out with the harmonic oscillator, but then made a jump going from harmonic oscillator of particles to creation annihilation operators of particles at a given position on the lattice. That's the change from particles to fields, because now you're talking about creation annihilation operators that specifically refer to a particular place in space. And that's the meaning of the word field. Field is a function of space. You are picking one particular position in space to talk about creation annihilation operator, and that's the field theory.
Right.
Does that answer your question?
Understood.
Okay, good.
Yes, yes. Right. Thank you.
Any further questions here? I see something in chat. I see you have to head out. Okay. Any further questions over here?
I also have a bit of a conceptual question.
Right,
just
Anna?
like about what it means to have like then the time evolution of like the creation or annihilation operator. Like I guess it's just like more likely to find particles in one place at time t, or like.
Right. So that's an excellent question too. So that basically boils down to question, you know, if you look at this Lagrangian, write down this wave equation as a classical Euler-Lagrange equation from this Lagrangian, what does it represent? We know now that psi represents particles because you can use it to create annihilated particles at any position you like in space. But what we don't know yet is what is actually the classical version of this. does it represent any wave you might see as a classical wave obeying this equation? And it turns out, and that was what I was meant to do with this poll, it turns out to give you actually a description of Bose-Einstein condensate of cold atoms. It's a specific systems where particles are bosons, and you cool the system to incredibly low temperatures, and then collection of atoms start to behave as if it is a classical wave. So that's a situation which is described by this classical wave equation, it turns out. And I'm going to show you the real experimental demonstration of this as we move on. Okay. Any further questions? Okay, so I finish it up now, and I see you on Friday. And if you have any questions, then ask me or Reggie, and so that I hope you can do the homework problem by Friday. See you and stay safe.